In this video, we're going to learn how to factor polynomial functions that we've never been able to factor before. So if we took a look at this polynomial function, using the techniques that we know, such as sum and product, decomposition, difference of squares, grouping, there isn't a way that we can factor this. So we're going to talk about something called the remainder theorem and the factor theorem in this video, which will give us the tools to be able to factor this. So first, let's do a quick exercise, which is review to determine the remainder when this guy here, which is our dividend, is divided by this guy here, which is our divisor. So we know that if the remainder is 0, then this is in fact a factor. And if the remainder is not 0, then x minus 2 is not a factor. So quickly, using any method you like, whether it's long division or synthetic division, quickly divide this guy into here. We can use synthetic division because our divisor is linear, so I'm going to use that. As we set up synthetic division, remember we're going to first put here the 0 or root of the divisor, which is going to be 2, and then we're going to put the coefficients of each of the terms in descending order of degrees, and in making sure that if there is a degree term missing, we're going to put a 0 coefficient. So we are going to have a 1 here, we've got a -2, -4, and 3. So quickly we're going to drop this guy down, multiply, we're going to get 2, add, we'll get 0, multiply, we have 0, add, we have -4, and multiply that, we've got -8. And when we add that together, we're going to get -5. So if you have any questions about the steps of synthetic division, take a look at one of the previous lessons that teaches or that talks about this. So we're left with these numbers here, so let's label them from right to left. So the first or the last number is going to be our remainder. This is going to be our constant term. This is going to be our x term, and this is going to be our x squared term, which means that we get a quotient of x squared minus 4 with a remainder of -5. So our conclusion then would be that this x minus 2 must not be a factor of this polynomial since its remainder isn't 0. So we're going to notice a strange pattern that occurs if we calculate f at 2. So let's define f first of all as this function here. That's not clear. And where does this 2 come from? Well, it's the root or the 0 of this divisor. So let's just try it. If we sub in 2 into our function, we have 2 to the power of 3 minus 2 squared minus 4 times 2 plus 3. And once you work out BEDMAS, we get -5. We've seen that -5 somewhere. It happens to be the remainder that we found when we divided them. So we can see that these numbers match. So we're starting to get the basics of the remainder theorem. The remainder theorem states that when a polynomial f at x is divided by x minus a, the remainder is equal to f at a. So we're talking about a linear divisor here, and if we plug in the 0 or the root of that divisor, we will get the remainder. So it's sort of like a shortcut. So back to the last question here, is x minus 2 a factor? Well, we already talked about that. How do we know? There's 2 different ways that we can prove it. One is that we can long divide or use synthetic division to divide it out. So one of the reasons is that there is no remainder when it's divided. A second way we can prove it is with the remainder theorem. So now that we've reviewed the remainder theorem, we know that we don't have to long divide to figure out the remainder. All we have to do is check what f at 2 is. And if f at 2 is not equal to 0, that means it can't be a factor because that means the remainder is not 0. Now that we know this theorem, we actually have all the tools we need to be able to factor this guy, because all we need to do is find a factor of it. Once we have a factor of it, we can divide that factor into this guy to get another factor. Just like if I started with 24 and I knew a factor of 24 was 4, I could just divide 4 into 24 and I would get 6. And now I have 2 factors of 24, and 24 is now factored. So can we apply that same idea to a polynomial? Well, what we do know about this guy is that x minus 2 is not a factor. And we have a shortcut for that now because of the remainder theorem. All we have to do is plug in 2. So doesn't it make sense that why don't we try plugging in some other numbers? And if we get that it equals 0, that must mean the remainder 0 and we found a factor. So what numbers do you want to try? Should we try 24? 100? Wouldn't it be easier just to try some really small ones? So let's try f at 1 and see what happens. So when we plug in f at 1, or when we plug 1 into the function, we get negative 2, which means that x minus 1 is not a factor. So let's try something different. How about negative 1? Let's try f at negative 1 next. Well, f at negative 1 gives us 4, which means that x plus 1 is also not a factor. What do you guys want to try next? Should we try 2? I'm going to save you some time. By the way, I'm going to show you a shortcut for which numbers that you should and should not try. Let's just skip ahead and try f at 3. And dun 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 dun, f at 3 happens to give us 0. So that means that when we divide x minus 3 into our divisor, into our dividend, we're going to get a remainder of 0, which means that it is a factor. So now that we have one factor, which is x minus 3, we can divide that guy into our dividend and find another factor. So I've set up some synthetic division because our divisor is linear. So I put our root 3, I put all of the coefficients here, and let's quickly use let's quickly do synthetic division. Try it on your own. Come back to the video when you're done. Once you finish synthetic division, or maybe you chose to do long division, you're going to get this as our answer. So our last number here is our remainder. Our remainder is 0. So we know that, we double check that x minus 3 is a factor because we got a remainder of 0. Here's our constant term, our x term, and our x squared term. So if I were to write that, what we got was the expression x squared plus x minus 1. So what's the relationship now between this guy here and x minus 3? Well, imagine if we did it with the number 24. One more time. So I know that 4 is a factor of 24. So when I divide it in, I get 6. Well, what's the relationship between 4 and 6 and 24? Well, we know that when we multiply these together, 6 and 4, we get 24, and there it is factored. So when we divided in x minus 3, we got this guy, which means that x minus 3 times this guy should give us our original function or dividend. So we can rewrite this dividend as x minus 3 times x squared plus x minus 1. So to really make sure we have this completely factored now, let's take a look at this guy. We can't do anything else with x minus 3, but is this guy factorable? Well, can we think of two numbers that multiply to -1 and add to 1? They do exist, but they're not whole numbers, so we can't do anything about it, or they're not integer values, so we can't factor this anymore, which means this is factored as much as possible. So now we have the tools to be able to take these polynomial crazy looking functions and factor them. So what we use is the factor theorem, which just piggybacks from what we know about the remainder theorem. So it just states that x minus a is a factor of f at x if and only if f at a, the root of this guy, is equal to 0. So from the remainder theorem, we know that if we get f at a equals 0, that means that multiplying this guy into f at x would give us a remainder of 0. So let's summarize the steps we use to factor that polynomial function. First, we got to find a 0a such that f at a equals 0. So we're using the remainder theorem. So we were just guessing and checking. I'm going to talk about a shortcut that we can use that eliminates a whole bunch of numbers that won't work. But once we have that factor, we are going to divide that factor into f at x to find another factor. And then we can just write that quotient as a product of those two factors, and we can continue factoring until we can't factor anymore. So that shortcut I was talking to you about, in order to quickly find this a value here so that we plug it in and we get a remainder of 0, If the leading coefficient of our polynomial function is 1, and that's what we were working with in the previous question, and that's what we're going to work with again here, the possible values of a are the positive and negative factors of the constant term. So if we take a look at this guy down here, our constant term is 24. If you take a look back at our previous example, the constant term was 3. So in the previous example, the only numbers that were going to work were factors of 3. And that was going to be plus or minus 1 or plus or minus 3, which is why 3 worked. For 24, we have our work cut out for us because there are lots of factors of 24. We can do plus or minus 1, plus or minus 2. Let's actually list them here. Okay, so here they all are. We have plus or minus 1, 2, 3, 4, 6, 8, 12, 24. So that's 1, 2, 3, 4, 5, 6, 7, 8 times 2. 16 factors we got to try. So this little trick sometimes really cuts our time down or sometimes makes it look like we've got an impossible mission ahead of us. So yes, there's 16 different factors that we could try, but also we can be smart about it looking at this. So just taking a look, we've got an x to the power of cubed, subtracting an x squared, subtracting another x, and then adding a 24. So if we were to put 24 into there, 24 cubed is a really, really large number, and there's no way that this guy is going to come down to 0. So let's go on the smaller numbers, and let's just check f at 1 and see what happens. So unfortunately, we didn't get lucky. F at 1 is equal to 18, which means that x minus 1 is not a factor. So let's try a few more. So let's try f at negative 1. We can try f at 2, f at negative 2. So you don't need to show your work for this. It's totally fine. Just like throw that into the calculator and write down your remainders right here. So try that on your own and come back to the video once you've got them. So if you got the same remainders as me, woohoo, and we hit the jackpot here. We found a factor. F at negative 2 is equal to 0. So therefore, using the remainder theorem, we know that x plus 2 must be a factor. So now that we've got a factor, we're home free because we can just divide this guy into here to get another factor. So try that on your own and come back to the video once you think you've got your other factor. So if you're back at this video, you're checking to make sure you got your other factor. So if we use synthetic division, here's what we got. So here's our remainder. Yes, we've proven again x plus 2 is a factor. Here's our constant term, our x term, and our x squared. So we know that we can take this guy here, which is what our quotient was, multiply it by the other factor, and we can get our original dividend. So here it is factored, but have we completely factored? Well, this x plus 2 is just linear. We can't factor it anymore. There's no common factor. But how about this guy? Can we factor this anymore? Are there two numbers that multiply to 12 and add to negative 7? Well, yes, there are. Those numbers would be negative 4 and negative 3. So we can rewrite this guy as x plus 2 and then factor this second trinomial as x minus 4 and x minus 3. So we can't break these factors up anymore. So now what we've factored this guy as much as possible and successfully factored this crazy looking cubic polynomial function. Before we move on and try a harder function, I just want to talk about this case 2. What if the leading coefficient is not 1? Well, then we've got to do a different trick to be able to find the different possibilities of A, and we're going to save that for another video. So if you're interested in that, take a look at that video. If you think you got the hang of this, let's try your skills at a quartic function. So now we're dealing with degree 4. We're going to do it exactly the same way. Let's find one factor of this guy using the remainder theorem, and then just keep dividing it in to find more and more factors. So we know that that A value has to be a factor of 6. So we have 8 possibilities for A. Be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Those are all the factors of 6. Side note, we also know we're dealing with this simple, easy case number 1, because our leading coefficient is 1. So let's go ahead and have a really good time plugging these numbers in. Hopefully we'll be lucky and find it out really fast. So see if you can try to figure it out on your own to test if you can figure out these factors. So if you're coming back to the video, hopefully you found a factor on your own. So what I plugged in was 1 and I got lucky. It gave me a remainder of 0. So I know that x minus 1 is a factor. So maybe you found a completely different one. So just a spoiler alert, if you had tried -2, that would have worked as well. Same with other ones. That just means you found different factors. Doesn't matter what factor you find, as long as you find a factor and divide it in, you're good. So the first one I found was x minus 1. If you found a different one, go with that one, divide that guy in. So I'm going to divide x minus 1 into our polynomial function. So go ahead and try that and come back to the video once you've done it. So if you factored correctly, you're going to get this quotient here, which means that we can write f at x now as a product of two factors that we found. So we found x minus 1, and now we found this other guy, x cubed minus 2x squared minus 5x plus 6. So have we factored this as much as possible? We factored it, but have we fully factored it? Well, x minus 1 can't be factored any smaller. Can we factor this guy? Well, doesn't this look super similar to an example we just worked on? This is just a cubic polynomial function. And unfortunately, we can't group anything. Nothing's going to come from grouping. So the only way we can factor this is using the factor theorem and the remainder theorem. So we're going to do it again. So we're going to use our cheat, which is we're going to try numbers that are factors of 6. So again, our a values can be all of these numbers, and see what we can find. All right. So a reminder, here's what our a values could be. I tried -2 and I got 0. Woohoo! Maybe you tried something else and got 0. Amazing, you found a different factor. So what I proved is that x plus 2 is also a factor. So x plus 2 is not only a factor of our big guy here, it's a factor of this guy right here. So let's find another factor. By now, remember, now I'm trying to break up this one here. I've already started to break up this guy into these two. Now I've got to keep breaking up this guy, and I found x plus 2 is a factor. So let's divide x plus 2 into this divisor and see if we can come up with another factor. Okay, my friends, if you factored this guy, if you divided x plus 2 into this guy, you should get this quotient, x squared minus 4x plus 3. So now, let's rewrite all the factors that we know of f at x. So I'm going to write this guy in black. Okay, so we know that the original factor that we multiplied in was, of course, x minus 1. And when we did that, we got x to the power of 3 minus 2x squared minus 5x plus 6. So that was this what we did right here. So we got to this point here. And now we broke this up even further. We realized we could break this up into x plus 2 times this. So let's keep breaking this up. So f at x is also equal to x minus 1. And then we broke this up into x minus 2 times this trinomial, x squared minus 4x plus 3. Can we break this up any more? Well, are there two numbers that multiply to 3 and add to -4? Well, of course there are. It's -1 and -3. So we can keep on factoring this guy. So we have f at x is equal to x minus 1 times x minus 2 times x minus 3 times another x minus 1. So we've got two x minus 1 factors, so we can just rewrite that as x minus 1 squared. So our final factored form of our equation is x minus 1 squared, x minus 2, x minus 3. And we are done. So now we know how to factor polynomial functions using the factor theorem.